Hi guys, in this tutorial we're going to look at how to determine the nth derivative of some mathematical expressions, of course if it exists. Now for our examples we're going to look at these expressions here. Now let's see how you are actually supposed to do that. Now it's important for you to practice as many expressions to see different types of expressions and how you predict their nth derivative, because sometimes all you need is just a trick, as you see for something like this. If you've seen it before, it becomes very easy for you to actually evaluate it. Now let's see what you're supposed to do, and these are some of the examples we're going to be using. We're going to be answering this same expression, predicting the nth derivative for the expressions given here. Let's look at the first one. Say you have an expression like this one, y is equals to 1 over x, and you're trying to predict what the nth derivative is. Well, for expressions like these, in as much as you can use quotient rule to differentiate, the best thing to use or to start with is using indices. And just take this up on top so that it becomes x minus 1. So of course, here the assumption is that you already know how to differentiate using product rule, chain rule, quotient rule, and so on. So just be seeing how we use those methods to predict the nth derivative. Now let's go right ahead and get the first derivative. So I'll be using y prime to mean dy dx. So in this case, the derivative of something like this will just multiply by negative 1 down. So this becomes x to the power negative 1 minus 1, which is negative 2. Next part, let's get the second derivative. The second derivative, y double prime, will be equals to, we're differentiating this now. So already we had this minus 1. We'll multiply it by the new power now, which is negative 2. And then we'll reduce that power by 1 again. So it becomes minus 3. We get the third. So the third derivative, just like before, minus 1 by negative 2 by negative 3 now, then x to the power minus 4. And we can get the fourth one. But at this point, let me say it like this. You should already start seeing the pattern that is taking place there. So you have minus 2 by minus 3 by minus 4. Then you have x to the power minus 4, minus 5 I mean, when you less 1 from minus 4. At this stage, you start seeing what is happening here. Of course, all these expressions can be written as negative 1. This is over x squared. This can be written as, it becomes positive of course, but this will be 2 over x to the power 3. And this will be negative again. This is going to be negative 6 over x to the 4. And lastly, this is going to be, that's going to be 6 by 4, which is positive 24 over x to the power 5. A pattern here started to show up. You want to control a number of things, 3 things to be specific. First and foremost, you observe that the negative comes, it goes, comes, it goes. So it has that thing to say it's not constantly there. It comes and goes. So you want to control the behavior, the presence of that negative. And to do that, let's write our expression for the nth derivative. So to control the negative for expressions like these, we use negative 1. But we want it to be present, then be absent, then present again. Now how do you do that? Well, we're going to use a power here. We know to say the negative raised to any power. It's either it's positive, not there, or negative, meaning it survives. So you want to raise it to the power n, either maybe n plus 1 or maybe n minus 1 or something like that. In this case, you see that n works just well because the values of n are natural numbers, 1, 2, 3, 4, and so on. So when n is 1, meaning you're getting the first derivative, and when you're getting the first derivative, you saw that the negative survives, and indeed, negative 1 to the power 1 is negative 1, so the negative will survive. But if you're getting the second derivative, n is 2, negative 1 to the power 2 is 1, positive 1, and indeed, the negative dies out for the second derivative. For the third, it survives, it's negative 1 to the power 3. And for the fourth, it dies out, it's negative 1 to the power 4, which is positive. After controlling the negative, the next thing that you want to control is the x in the denominator. You see that it's always present, but the only thing changing is its power. Because you see, here it's squared, here it's cubed, here it's 4, here it's 5. Now again, you want to relate this power to the order of the derivative. In this case, you are getting the first derivative. Look at that power. It was 1 more than the first derivative. By the time you're getting the second derivative, again, the power of x here is 1 more than that second derivative. Just the order itself plus 1. By the time you get in the third, again you're seeing the power here is 4, 1 more than that power, that order. By the time you get in the fourth, again that is a 5, 1 more than the 4. In other words, we can conclude that what is in the denominator, it's always x, but it's raised to a power such that the power is the order of which we're evaluating, but just 1 more, which is plus 1. So that this is going to control what comes in the denominator. The last thing we want to control is the value that goes in the numerator. Now, how do we predict that? Well, to understand what is happening there, we look at these values here. We look at these values. We have 1 times 2 times 3 times 4. Here then we have 1 times 2 times 3, then 1 times 2, then 1. Well, these can be related to the powers themselves. Of course, I'm not looking at the negatives, already taking care of the negatives. So just looking at the numbers there. When the order was 4, when it was the fourth derivative, we had 4 times 3 times 2 times 1. When it was the third derivative, we had 3 times 2 times 1. When it was the second derivative, we had 2 times 1. When it was the first derivative, we had just 1. In other words, you should see that this is a factorial. For the fourth derivative, it's 4 factorial. For the third, 3 factorial. For the second, 2 factorial. Meaning, for the fifth, it will be 5 factorial. For the sixth, 6 factorial. In other words, this is n factorial. So, from here, this is the expression for the nth derivative for our earlier expression. Okay, with this one sorted out, let's move on and look at our next example. What if you had something like this? And again, they want you to predict the nth derivative. How do you do that? Well, in this case, just like before, you want to start by differentiating a couple of times, then trying to see the behavior. But for this, for us to differentiate this, first we're going to use quotient rule. So let's say u is equals to 1 plus x, so that the derivative of u, which is u prime, will be equals to just 1. Then if we let v be equals to x minus 1, the derivative of v prime, will also be equals to 1. Then we can say y prime, the derivative of y, will be equals to, we have v, then u prime, minus u, then v prime, divided by v squared, by quotient rule, of course. If we substitute, v is x minus 1, u prime is 1, so minus, then we have u is 1 plus x, then v prime is 1 again, so this is over v squared, and our v is x minus 1 squared. When you're dealing with these expressions, don't oversimplify. Sometimes when you simplify too much, it might be very hard for you to see. So I will not simplify this. I'll leave it like that. But I will simplify the numerator. For the numerator, look at what we end up with. When I remove the brackets, we now have x minus 1. Then we have minus 1. Then minus x. This is over x minus 1 squared. From here, y prime ends up being equal to the x, and the x will subtract out. Then we have minus 2 over x minus 1, but it just has to be squared. So this is what our first derivative looks like. Now I want a number of them. I want to get the second, third, and so on, so that we can try to predict the pattern. So how do we do that? Well, for this one, we no longer have to use quotient rule. It can work, but there are easier methods. So we're going to use indices again to rewrite this expression as 2. Then we're going to have x minus 1, then to the power minus 2. So that's the expression we're going to differentiate. The second derivative becomes minus 2, but just multiplied by the power, which is minus 2, then multiplying x minus 1 raised to the power minus 2 minus 1, which becomes minus 3. Then the derivative of the inside is just a 1, so no need for us to write it there. Then of course, if you wanted to write this in a simpler way, this just becomes the product on top will be a 4, and then down we're going to have x minus 1 to the power 3. The next one, the third derivative, we just have to differentiate this again. So of course, we just multiply by that power minus 3, so that we have minus 2 here, now minus 3, then x minus 1, then minus 4. Of course, if we write it in the other way, minus 2, 4, minus 3, 12. So we have minus 12. Then we have x minus 1 to the power 4. If we were to get the fourth derivative, now this becomes, so again, we just differentiate this expression. So this is going to be minus 2 by minus 2 by minus 3 by minus 4. Then x minus 1 to the power minus 5. Again, the derivative of the inside is just a 1, so we're leaving it out. This is now just going to be whatever we had earlier, just multiplied by 4, which becomes 48. Now, it will be positive. Then x minus 1 to the power 5. We can do this one more time, but already a pattern is starting to show here. Let's see what we have to do here. First and foremost, again, there's a negative that we have to control. It's present, unlike before. It starts, so actually just like before, it's present, it's not there, it's present, it's not there. So we're seeing that it's present when the power is even, and it's absent. No, it's present when the power is odd, and it's absent when the power is even. In other words, to predict the nth derivative for the negative part, it's easy. Again, we have negative 1, just raised to the power n. When n is 1, you're going to have negative present. When n is 2, the negative will be squared out. When n is 3, the negative will survive. When n is 4, to be squared out again. So that is controlled. The next thing again you want to control is that denominator. Again, by comparison, we see to say that the power of the denominator is always 1 more than the order we are dealing with. But always the denominator is x minus 1, throughout it's x minus 1. It's just the power that keeps changing. It's 1 more than the order. So we always have x minus 1, but the power will always be n plus 1 more than the one we're dealing with. The next thing that we have to control is the numerator, not the negative part, just the value itself. We have 48, 12, 4, and 2. Is there a pattern to this? Well, let's look at this. Again, you always want to look out for that factorial. Is it possible for you to take advantage of it? So this is 4. When the order is 4, I am starting from 4. So I am multiplying 4 times 3 times 2. Well, even if there's a 2 that comes next, you know a factorial, it's possible that you can even squeeze in a 1 here. So that this is actually 4 factorial. But it will mean that the 4 factorial is actually just being multiplied by 2. Well, let's see if this can be extended to this one. The order here is 3. Is this a 3 factorial? It's a 3 times 2. Well, just like before, we can squeeze in a 1 here. So that this is 3 factorial, but we're seeing that again we're multiplying by 2. When we come this side again, we're seeing this is 2 factorial, but we're still multiplying by 2. This is 1 factorial, but just multiplied by 2. In other words, we can see that this is 2, but multiplying n factorial. Now, this predicts the nth derivative. We can even try it for the fourth one. For the fourth one, we have y, the fourth. Let's see if it works. We have negative 1 raised to the power 4. Then we have 2, then 4 factorial. Then divided by x minus 1 to the power 4 plus 1. Will it work? Negative 1 to the power 4 is positive 1, so that dies out. Then you have 4 factorial, that's 2. Multiplying 4 factorial, that's 4 times 3 times 2 times 1. Divided by x minus 1 to the power 5. Well, the denominator is sorted out. How about this? 4 times 3, that's 12. 12 times 2, that's 24. 24 times 2, that's 48. We have 48 over x minus 1 to the power 5. You can try it out. This value that we've got is the same as the one we got when we just went the direct way of differentiating. You can try it for the fifth derivative. Differentiate it the normal way using this and try to get it using our prediction here. So this is how we approach this one. Now trig ratios can be a little bit tricky, but again, let me show you how you are supposed to approach them. So suppose you have a trig function. Suppose you have a trig function like this one. And again, we want to see how you can come up with an expression for the nth derivative of something like this one. Now the argument here can be anything really, but in this case, for example, we're just using this one. Just like before, the assumption here is that you know how to differentiate a trig function, but to get the final answer here, you need to know one simple identity. We'll bring it when we need it. Okay, let's get started. The first derivative, of course, for trig functions, first differentiate the function. So the derivative of sine is cos, so the argument doesn't change. Now differentiate the argument. The derivative of 2x is going to be 2, so the 2 comes here, the x is still here. Now let's try the second derivative. For the second derivative, y double prime, what we get here is, let me just move this a little bit. For the second derivative, again, we have this 2 here. Now we'll differentiate the cos 2x. So the derivative of cos is negative sine. So we're going to have negative sine 2x. Then the derivative of the argument, again, it's 2. So we still have times 2. By the time we're going to the third derivative, we differentiate the sign, we get cos. So we still have the 2 and the 2. But now when you differentiate, we get cos, so the negative still comes here. So you have cos 2x. And when you differentiate the argument here, we get 2 again. We should see what is happening to the 2 there. But let's just get the fourth one as the last one. The fourth derivative. Again, when you differentiate this, now we have 2 times 2 times 2. The derivative of cos is going to be negative sine again. So the negative in this one will cancel out. So we have sine now. The derivative of the argument is going to be 2 again. So times 2. Well, if we look at this, we can even start predicting the nth derivative. Well, the first thing that you see here is that the 2 here keeps multiplying itself. How many times? The number of the order of the derivative. When the order was 3, we multiplied 2 times 2 times 2. 2 by itself 3 times. When the order was 2, we multiplied 2 times 2. 2 by itself twice. When the order was 1, we just multiplied 2 by 1. In other words, to control this number outside here, all we need is 2 raised to the power n. That sorts out the 2 outside. The next thing that we want to predict here is, what is this side? Here we have cos, here we have negative sine, here we have negative cos, here we have positive sine. How do we control this part? Well, this is where now you need to understand. We need to go to a double angle identity. And in this case, we'll use the one for sine. So you have to recall that if we had, say, sine A plus B, this is equal to sine A cos B plus sine B and cos A. So this is a double angle identity. But here is the thing. In this case, one of the angles has to be the argument that never changes here, the 2x. So that has to be one of the angles there. So one of the angles must be the 2x. So the 2x always survives there. So one of these angles, A or B, has to be the 2x. Doesn't matter which one. So in this case, let's give the 2x to the first one. 2x. Now the next thing is, we want to know what angle must we add to the 2x such that, for example, if you look at the first one here, y prime, you want to pick an angle such that when you replace it in this expression, your answer must be cos 2x. Your answer must be this, cos 2x. Now, what do I mean? I want to know what this one here must be, such that when I plug it in this expression, my answer must be cos 2x. Let me just put something unknown here, like I can put t. So by double angle identity, this one here, it becomes sine 2x, then cos that angle t, then plus, this is sine t, then cos 2x. Now, if the answer to this expression has to be cos 2x, notice that it's like this has to give us 0. But sine 2x should not be the one determining that. Our determining factor has to be cos t, or in other words, the angle t there. It must ensure that this term gives us 0. And when you put it here, it must ensure that this gives us a positive 1, so that the only answer we remain with is cos 2x. So all you're thinking of now is, for what angle t here, what angle must we have here? Of course, that angle has to be 0, so that this whole thing must vanish. But it has to be an angle such that when we plug it this side, it gives us a 1, a positive 1. Notice that if you start with cos will be equals to 0 if the angle is 90 degrees, or let me say pi over 2. It will also give you 0 if the angle is 270. So it will give you 90, to give you 0 at 90, and it will also give you 0 at 270 degrees. But if you used 270, sine 270 will be negative 1. In this case, we want positive 1. In other words, we're going to go with 90, because we know sine 90 is 1. So, in other words, we're going to move with pi over 2, which is 90. So we now know what our angle here is. This has to be pi over 2. So this is pi over 2, 90 degrees, such that cos pi over 2 has to be 0, which will make all this be 0. And if we do it this side, sine pi over 2, the answer will be cos 2x. So with that in mind, we then replace where we have cos 2x here. We can write this expression as just 2, then sine 2x plus pi over 2. Now, I want to do the same thing with everything that follows here. And how will it be? Well, if you look at, so I've already used up this one here. So let me just write it as a 4. So this is a 4. And I can move this so that I have more space. And we can do the same thing here. This is an 8. And this can come here. And this is going to be 16. And so that this can move. Okay. Now, for this one again, we want to do the same thing. We're still using the same identity. And now I hope you're getting the trick of what is happening here. So again, we want to know what the angle here must be. if now the answer, look at this, now the answer has changed. For the second derivative, the answer must be negative sine 2x. So the answer has to be negative sine 2x. In other words, what this is telling us is that this has to be the thing that survives. What has to be the angle here? If what survives must be sine 2x, but it should be negative. Where will the negative come from? It will come from cos here. And it implies that this part here must give us 0. For this to be 0, it means that whatever the angle here is should ensure that sine gives us 0. So we'll start with this one. When does sine give us 0? Well, sine will give us 0 if theta is equals to 0 or if theta is equals to 180 degrees. But we also want the same thing to give us negative 1. When we put it here, cos 0 is positive 1, so it won't give us that. Instead, we'll go with cos 180. 180 in radians is just pi. So in other words, the angle here must be pi. You can try it. If this angle is pi here, what will happen is that then this is also pi and this is also pi. What will happen is that sine pi is 0, this whole thing becomes 0. But cos pi is negative 1, so that the answer becomes negative sine x. What does this do? Well, when we bring it here, now we want to write it in the same way. So we're going to have 4, but now we have sine. So I want to say 2x plus pi. But we want to be consistent. Look at this, we had this 2 here. So if I wanted to make sure that I always have a 2, oh, I can leave it like this first. I can leave it like this. Let me show you that that 2 actually has to be there. But first, to show you that, we'll do this one. You have to see that this expression, especially this part here, sine 2x plus pi, it has the same influence as negative sine 2x, as you saw here from this expression. Okay, the next part, we now want to look at the third derivative. Well, try to see if you can predict the behavior, and let's see if you can pull it out, and try to see if you can use the double angle identity to show that this will be equals to sine. Now it will be 2x, to still be plus, but now it will be 3 pi over 2. This is what you're going to have. Try to see if you can use this double angle identity. Same thinking process. Predict what this will be. If what should survive, when you look at this, what should survive? Over this one here. If what should survive is minus cos 2x. If the one surviving is the 2x but just negative, it implies that the angle that comes here has to give us negative 1. Sine gives us negative 1 at, it gives us 1 at 90 and at 270. It will only give you negative 1 at 270, and 270 is 3 pi over 2. And if you tried cos 270, it will give you 0, meaning this will die out, and this will give you negative 1, ensuring that the answer is negative cos 2x. That is how we end up with this one. At this stage, you now notice that the 2 is always in the denominator. Because the 2 is always in the denominator, and want to make sure that this flows, so even here, I'll put this over 2. But I don't want to change everything or anything. By putting a 2 here, I'll include a 2 on top. So this is 2 over 2, which is still just pi. When you look at this, a pattern has already been created. Notice that the order of the derivative here has to do with this one on top here. If this is 2, then the pi is being multiplied by 2. If this is 1, then the pi is being multiplied by 1. If this is 3, the pi is being multiplied by 3. In the same way, you should see that if you tried this one, it will be 16, then sine 2 pi, then plus 4 pi over 2. You should see that this is what you're going to have. So this can continue. In other words, the nth derivative now can be obtained by just evaluating 2 to the power n to control the coefficient, then sine, this will be 2x, never changes, but plus the order of the derivative, pi, but divided by 2. This is what will give us the nth derivative. Okay, so I'll give you guys this. This is the third one, but I think we've lasted long enough. 30 minutes is a lot of time. So end here. I'll let you guys try out this one, and let's see what you guys are going to find. If you guys want to see more math videos, leave a like to this video, comment in the comment section, and we'll give you guys more. Now guys, we'll see you in the next tutorial.